Hello, everybody. Welcome to the high power conversion section of the Design It Day webinar, sponsored by the Diageo Group. I'm Alan Cooper, a senior electronics and electrical engineer with experience in vehicle systems. To consider high power conversion, we will touch on the current market conditions. I'm going to investigate the technology using a bidirectional AC to DC converter coupled with a bidirectional DC to DC charger. We'll touch on the market presence. We'll look at the design from a top level, from an overview of top level. We've got the design split into 4 stages, so we can actually drill down and look at the components in detail. Once complete, we'll do a summary and then open up for Q&A. Is silicon dead? Absolutely not. But the challenges of the high power niche market covering automotive, energy, and industrial sectors have discovered technology which addresses these challenges and provides design opportunities to create commercially viable solutions. So what is the technology? Technology is the collaboration of semiconductor and RLC component technologies. Silicon carbide and gallium nitride provide the semiconductor technological advances, and the necessary leading edge RLC components are available via the umbrella of the Diageo Group. Wide-bandgap semiconductors. The difference between silicon and WBG, the conversion efficiency is significant in terms of its difference. And there are three main areas that the WBG provide a significant advantage, and that is it allows a higher frequency, higher voltage, and higher temperature. And we'll consider these through all of the components that we actually go through with the design. So if you look at the capacitance and versus power equation that's at the top of the right-hand slide there, you can see that the frequency is the capacitance is inversely proportional to the frequency, so that as the frequency goes up, the actual capacitance value can actually go down. So that when we're at the lower frequencies in the silicon region, the film and electrolytic type capacitances were the ones that were actually the ones that we needed to use. As we increase the frequencies, we can actually start to work towards the ceramic capacitors. And that basically means we can get smaller, lower ESR, lower ESL, high DVDT, high DIVDT, and current capability. Also, in terms of the higher operating voltages, that basically means that if you consider the half CV squared equation, that basically we're looking at a V squared operation. So the higher the voltages we can get to, the better it is in terms of the amount of energy that we can actually use. And also, if we're actually going to be, if we're going to move energy backwards and forwards at high frequencies, then the devices, the wide bandgap devices need to cater for higher temperatures. We typically at the moment operate at 105 to 125 degrees C. We're looking at temperatures of 150 to 200 degrees C. And while the wide bandgap devices are looking to support those things, the RLCs need to be able to do the same thing. So let's just take that through and have a look at the overview of what we're actually talking about. Okay, so now I put my laser pointer on and I can actually take you through this, take you through the design. So we actually have from here on the left-hand side, the AC at 380 volts, and we'll take it through to this point here at 700 volts DC. So I've got it, at this point, I've got the AC to DC conversion taking place. I've taken it from here, basically filtered it, switching it into DC. So I've basically taken the AC to DC, and therefore, because I've got the switches there and therefore the control, I can switch it back again to take it from DC to AC. And by using the switches, I can actually change effectively what the AC is if I went back in the opposite direction. So having got the DC at 700 volts, I've then got switches, and I've got an LLC converter, and I can actually then switch the DC from the left side into the LLC environment here on the primary side of the transformer, and that can actually transfer the energy through its self-resonating frequency to the right-hand side. I can then switch it again and pump it into the two capacitors at the other side to provide me again a different voltage. So as you can see, I've gone from AC to DC, DC via the LLC to DC using switches and pumping it into two capacitors here to provide me a DC level. And that DC level with those capacitors and the inductor is signal conditioned to provide the correct or provide a reasonable signal to actually charge the battery. So this is what I call my Mona Lisa moment, right down here in the middle. If I actually flip the capacitors over through this line over to this side, then I can flip it either this way or that way, and that what gives me the bidirectionality. So the Mona Lisa being symmetrical, this is what the symmetrical side of the design actually provides. So let's move on. What I've done is that as I said, we've split it into sections. There's the EMI filter, there's a power factor correction section, there's the DC to DC translation. That includes the LLC resonant circuit, including the CR, LR, and LM all together, both sides mirrored with one another. And that then goes into the filter to condition the signal to actually charge the battery. So let's go into it into greater detail. As you note, as I go through this, you'll see that the components will appear in boxes, and they've got a colored boundary. That colored boundary relates to the highlighted components as they come up. So as you can see, the safety caps, we have safety caps connected between line to line and also between line and chassis. We've got common mode chokes. And then we've got in Delta, we got the AC harmonic filter that comes in a Delta configuration. Then moving into the power factor correction section. And what this does is it provides you with inductive components such that you can actually balance the power factor and bring it closer to 1, and therefore transfer as much real power as you can to the battery. And then you also need to measure the current that you actually are pushing through, so you can actually control it with the switches. And then you've got the snubbers across the actual switches. If you switch anything, even at home, you'll find that sometimes it will spark. And the idea of the snubber is to remove those sparks and prevent any damage to the silicon switches, the FETs that are there, to provide those with protection. In terms of isolation transformers, we use those to actually drive the switches, and the isolation is a method of actually providing isolation from your driving circuits, so you don't affect or upset your driving circuits, and also you don't affect the actual switches themselves and cause them damage. You pump that energy into the two capacitors, and that's commonly known as the DC link. I'm sure you're familiar with that term. And there's the two capacitors there, and we will go through various components and various sorts of capacitors that are available to use for DC links. And as you can see, they're surrounded by resistors, and the resistors are used to balance out the leakage currents from the capacitors and get a balanced voltage. Moving into the DC area, again, we're back to the snubbers on the switches. We need to protect the switches. We've also got the isolation transformers to drive them, and the current sensors to understand what current it is, so we can put that in a control system and actually provide the control through the resonant tank. We then move into the LLC portion of the self-resonating frequency in terms of how to actually take the energy from one side to the other. The as the capacitance, you can see is the CR aspect of it. And then we have the power transformer. And the power transformer usually has the inductive, the LR portion of the LLC tank built into the actual transformer. And then we'll move on to the output inductors in terms of the signal conditioning for charging the battery. We then have films. We then have the output capacitors, very similar to the capacitor that we use for the DC link. And we have the power resistors to go around those capacitors to actually balance out the leakage currents from those particular capacitors. So having gone through the overview, let's take it through each stage and go into more detail in the actual components themselves. So here we are, first stage. Talk about safety capacitors, again, between the line to line and the line to ground or line to chassis. We have the common mode choke to remove the common mode signals that we don't really need. We have the AC harmonic filters to actually remove noise on the AC lines and produce those. So we have the X capacitors, the line to neutral or line to line. The design doesn't actually show a neutral line, but that's not necessarily important. But the X capacitors will work for both line to line and line to neutral. We also have the Y capacitors. The X capacitors, as you can see in there, you've got two different flavors, two different varieties in terms of X1 and X2, offering two different results. The peak that you can actually get there is 2.5 kV. For the Y capacitors, you've got a range of 150 volts AC and 500 volts AC with peaks of 5 kV and 8 kV. Let's look at the actual capacitors themselves. So for the X capacitors, you'll see with the theme of this presentation that we will start with series, and usually the component on the left-hand side is the component that we originally created. So the R46 is the initial component that we used, and the R46H is if you like, a sister component, and that is, as you notice with the H, it goes, the R46 is 110C, and the H usually includes the higher temperature, which is 125. So progressing on, we go to the R52. That's a mini version of the R46. It has greater capability in terms of the harsh environment, and it's also small. Again, with the R53, again, it's small in terms of what it does in comparison to the R46. It goes even further in terms of the harsh environment capability that it has, and it's gone from the grade 2B to the grade 3B. And as you can see, the progression goes further to the right. Let's look at the Y capacitors. The Y capacitor here in terms of the Y2 is 250 volts AC, and it's got high DVDT, which is 2000 volts per microsecond, which is really significant. And then they've got the R41 and the R41T in terms of the greater capability in terms of their harsh environment. So let's move on to the chokes. What the choke basically is trying to do is take the common mode noise, and the way that the chokes are actually wound is such that they're wound in antiphase, so the actual common mode noise is actually neutralized. What you need to know when you're choosing the common mode choke is the impedance, the frequency range, and the current capability. Here are some examples of the common mode chokes, and you can actually get the rated from 300 milliamps to 19 amps. The common mode chokes up to 50 amps. Also notice you can get the low profile, and you can get custom solutions. So you can get almost any flavor of choke that you want. We have it, or we can make it for you. More common mode chokes. If you look at this, there's a range that are offered from the Pulse. The Slick series are up to 40 amps and going up to 80 amps. Note that the isolation goes from 500 volts up to 5 kilovolts, and you can actually get them surface mount or through hole platforms, and they can be customized to your specific needs, and that's often the case. Let's move on to the harmonic filters. What you've actually got here is you've got the capacitors arranged in either delta or star format, and as you can see, the connections give you a different voltages. The star format gives you 330 volts. The delta is therefore 40 volts. The reason it's a delta is because of the capital letter of the Greek alphabet is a triangle, and that's what delta. So that's why it has that delta arrangement. But it's about these capacitors about removing that horrible noise that looks up on that top right-hand graph. Then moving on to further AC filters, the C4A series. Their significance in terms of their voltage and also the longevity in terms of the THB. It's a significant 1,000 hours. That's actually a significant advantage for you. Also, then a really large version is the C44P, going up to 2,300 volts DC. Okay, let's move on to the power factor correction section. What this does is it takes inductors, current sensors, snubbers, and isolation transformers, and the DC link, and the power resistors. So what the power factor correction does is the inductor basically takes the reactive elements of this particular stage and tries to neutralize, if you like, the reactive elements, so that the power factor itself is close to 1. What that allows you to do is transfer the energy, transfer real energy to the output, and neutralize the effect of energy bouncing back between the reactive components. The current sensors are there to measure the current, so you can actually control the current that's actually going into the two capacitors into the DC link. The switches are there to chop that up in terms of how you want to actually fill the capacitors. The capacitors again will need protection with the snubbers. We'll talk about that in a minute, and also the isolation transformers and the DC link. Let's move on. High power. Here we talk about the actual inductors that are available. We have various inductors in terms of choice to do that in terms of the high power. We have this current a range of current sensors in terms of either high frequency available from Pulse again, which range from 10 amps up to 30 amps, and also the isolation requirements, as I said before, it goes from 500 volts up to 5 kilovolts. They're available in surface mount and through hole in terms of custom, and again, custom may often be required what you need. Other current sensors, these are single wire current sensors, and they actually they're available in different forms and different options, as you can see there. We talk about the snubber capacitor. What the snubber capacitor does for the insulated gate bipolar transformer by transistor is that basically will have some form of inductance, and as you switch the switches to remove that spark, if you like, or that energy, and prevent it to actually go in the actual switch, you use a snubber capacitor to nullify that the effect. So what do you use for snubber capacitors? We're actually using the R75. Again, the initial component is the R75. It's got its best self-healing capability. It's probably one of the least expensive, and it's actually 105C. And goes from -55 to 105C. No, so that's probably, if you can actually use this and meets your requirements, this is the device that you need. However, if you've got a requirement that says that you need a higher temperature and greater robustness, perhaps consider the R75H. As before, the H indicates the higher temperature, and that's up to 125C. The R76 has greater dV by dt capability, So as you see, going from left to right, each time we just tweak it somewhat in terms of the different capabilities to meet your particular requirements. The R76, basically high temperature. The R73 is the highest dV by dt and highest current capability. It's also the highest price, but it depends what your requirements are. And we've got components that meet most of the requirements that you will have. Another technology to use for your snubber capacitors are the ceramics. And as you can see that they go from the voltage range is up to 3,000 volts. We actually have one under development at the moment up to 10,000 volts. As you remember, we were going through the wideband gap. Their voltages were going up to 1,200 to 1,700 volts. So you actually need some significant RLC components to support that type of activity. As you find with the KC link, you can see that they will have extremely high ripple and low ESL. In other words, the ESL helps in terms of the balance with the inductance, and also the beauty of these particular components is the lack of shift, if you like. In other words, the capacitance value remains the same over a great temperature range as it does over a voltage range. It also has a flex termination available, and what that basically means is that the way we've connected the hard ceramic to the actual terminal connection has got a special connection mechanism such that it actually is more flexible and therefore less brittle in terms of it making it work. Talking some about in terms of the gate drivers, in terms of in terms of the isolation transformers, again we have a range of these transformers, especially from Pulse, and they're going from 2.5 kV up to 5 kV, and they're small and they're actually very useful in terms of being able to drive those wide bandgap semiconductors, again available in custom surface mount and through hole versions. Let's talk about the DC link capacitor. In terms of this, if you actually consider the formula that's in front of you, it's basically the half CV squared formula. And what that is just trying to calculate the energy. So the power times the time gives you the energy, and the half CV on the other side, if you rearrange it, gives you the capacitance that you actually need. And what that actually does is that the ripple that's occurring when you're actually doing when you're chopping up the AC and putting it into DC, the DC link provides the energy in between the actual ripple of those waves, as you can see in the voltage side, that the energy is provided by this DC link capacitor. So when you're choosing it and designing it, you need sufficient ripple current capability. And what that means is that you need to have lots of current into the device, but that also means that current hits the resistance of the capacitor or the ESR, the equivalent series resistance. So you want to have low series resistance. So let's look at some devices that can actually address those things. Again, we're back to the left to right technique for presentation. We got the C4A series. The Q was the original device. We then go from there to the mini, and then to the long life one, which is the QP. We then go into the high ripple current capability and high robustness in terms of what it's actually trying to do with the C4AU, and then you go to the prize at the far end is basically the first to market with the C4AK, and that's a high current capability. And it says, and it talks about the maximum temperature at 135. Also notice that the high voltage and long life is at actually 125 C. So that is significant in terms of what it does, and also having a high temperature of survival at 135 degrees C. Plus you've actually got the THB at 85, 1000 hours. Again, a significant environmental capability. Let's move on to the C4E. What this is essentially a customized DC link capacitor. It's 1800 volts. It's 18,000 microfarads, 1800 microfarads, should I say, and with a maximum temperature 105. These are designed at customers' requests in terms of what they need, so we can actually not just provide off-the-shelf components that we believe will actually meet requirements. There are other ones that are specific to customers and what they need, and it can be developed to provide results and answers for them. The C44 again is a significantly large capacitor that actually has a very high current capability and a capacitance of up to 3,000 microfarads. Let's move on to another style of capacitor, and that is which is becoming popular, especially in the automotive industry. It's particularly the snap-in ones, and the press fit not so much. Why do we have these? Because basically there's no soldering, quick exchange, eliminates cold whelm, so it's very easy to use to manufacture. You don't have a lot of the other manufacturing capabilities, and also you avoid the problems of soldering, washing, and field exchanges are actually very easy. You've also got others with screw terminals, and these ones with screw terminals have been developed to have a low inductance screw terminal. So you've almost reduced the screw terminal inductance by 50%. It's actually about 40% in terms of that. So you can actually have capacitance with low inductance as well. Moving on, there is another choice as well, which is the aluminium electric capacitor, aluminium electrolytic capacitor, and that has a vibration resistance of up to 40 G, which is actually significant, especially in the automotive industry. Also, that the shape of it lends itself to economical space usage in terms of the designs. Power resistors, as we saw in the diagrams, the resistors are used across the DC link capacitors such that they actually balance out the capacitors and actually remove the leakage differentials between the two capacitors and provide you with a voltage where the voltage is actually balanced on both of the capacitors. So let's move on to the third stage. The third stage is the DC-DC. Well, we've got snubber capacitors, isolation transformers, and current sensors. I'm not going to dwell on those too much for the simple reason that we've already talked about those in the power factor correction section. And we'll look at the resonant capacitors and the power transformers, which make up part of the tank circuit. So as we've said, we've talked about snubber capacitors. We've talked about the snubber capacitor capability and the ceramic capacitor capability in terms of applying those to the switches, and the gate transformers designed to actually drive the switches and isolate the driving circuits from the actual switches themselves, and therefore protect both the switch and the driving circuit. We need to understand what the current is, and that's used by the current magnetics, which we've already talked about. We'll move on to the LLC resonant circuit. This is the tank circuit. It's a self-resonating circuit, and what it requires is the design of the capacitance. And the beauty of this is that because of having the self-resonating mechanism, and therefore zero volt switching, you get very low losses in terms of what it is, and high efficiencies. And the other one that's really worthy of note is the high frequency operation. As we talked right at the beginning, is that higher the frequencies, we're going to get lower capacitances, or lower capacitances that we can actually use. But that makes that you have to be careful in terms of how you choose your resonant capacitors. So it can actually work for a high voltage or a low voltage operation, but you do need low ESR because you're actually pumping energy in and out of the capacitor, and that means it's going to hit the resistance, and therefore the lower the resistance that you have, the less energy you're going to lose actually warming up the capacitor, and you can pass that energy onto the battery. that means the capability, you need a capacitance to have high ripple current capability. And again, the importance of the capacitance. The capacitance stability basically means is the capacitance value remains the same over a wide range of voltage and temperature, such that your design, such that your design is actually constant, and you don't have to make alterations to the design because of it. The frequency range for here is basically 100 kilohertz to a few megahertz, and that basically takes your design into a region where the energy, it takes it into a region where the energy is easily transferred. What are the requirements? As we've just talked about, the most important ones are the stability over temperature range, over voltage range, low ESR, and a high capability with AC current. What technologies address this? Let's talk about the power film technology in terms of what it particularly does. As you can see, the life versus the temperature for this particular type of technology is great if you can actually keep in the into the low temperature. Well, I say low temperatures if the ambient temperature is below 70. And the same in terms of the life temperature graph right at the top there. You can actually see that the life expectancy is 100,000 hours, but as you get into the if you get into the temperature range of 100 and 105, the life expectancy drops significantly. But if you can actually maintain below that thing, this is a good technology to use. Resonant field capacitor, we've talked about the R75 before. And R75, R75H, R76, all those capabilities we've talked about, but it's still there and available for the resonant capacitor as well as the DC link capacitor. In terms of dielectric, what's important to notice here is the dielectric class 1, which is the C0G and the U2J. What is that at the frequency of 100 kilohertz up towards a megahertz, as you can see in the red. Let's move this and show you across here that this is actually around about, if you look for the value on the left hand side, it's around 11 milliohms, and it's actually pretty constant. The rest of this here in terms of what this is, please don't worry about that. It's because you can't, it's very difficult to actually measure the C0Gs at these sorts of values, and that's why you get the noise, if you like, on the actual on the graph. So as you can see from the class 2 dielectric, the X7R, it has a higher ESR, and that's 650 milliohms. And it does come down, but it's still higher. The other thing that you need to make observation is the is the actual temperature rise that you can see with the C0G and the U2J, that over the different ripple currents that you can actually get to. C0G is looking at 10 amps in terms of ripple capability, and the temperature rise is only 10 degrees C, which is really a great result. The X7R ripple current it can cope with is down to probably 3 or 4 amps before the temperature starts to soar, but it's still available in terms of higher capacitance. The C0G is lower capacitance, but actually can cope with larger ripple currents, and has a constant ESR over a great range of frequency. Then we move on to the ceramic capacitor in terms of its use. With this particular one, we can use it as it's shown there, both as a snubber and as a resonant. The KC link has a really high ripple current capability, as you can see on the right hand side. The current capability, we're talking up to 16, 18 amps, and also that you've got a negligible capacitance shift and negligible voltage shift. And as we showed in the previous slide, we're talking about 11 milliohms ESR, and they are wonderful properties to actually have. If there's a concern about the actual capacitance size itself, we have something called note the KC link, DC link. So in other words, if you want to do DC link, the K, we can say it's Kemet C link, if you like, and that's how you can relate to the DC link and know which component to come and look for. If you need to have more capacitance, you can use the connect technology that we have. There's a way of actually connecting them very simply together with a tin copper substance that actually allows you to effectively weld them together and provide you with a greater capacitance. So you can stack them, you can do stack sizes to 2 to 4 high and provide significant capacitance that way. So when you're considering the AC voltages, I'm going to put both of the rules up here at the same time. As you can see from the left-hand graph, the rule number 1, the very easiest way to do it is that your DC rated voltage needs to be higher than the DC voltage plus the peak of the AC voltage. In other words, your blue dotted line needs to be lower than the red dotted line, and the formula is there for you. If you want to use, and then also rule 2, you need to consider the AC side of things, and that means that your DC half your DC rated voltage needs to be greater than the actual peak of your AC voltage. If you want to convert it into RMS, then the conversion's there. It's that root 2 factor that goes with it, and those are the 2 things that you actually need to do. It says memorize the AC voltage rule. Please do that. Please adopt it, because it actually makes life a lot easier when you're actually designing. So what the capacitor technologies, what is the best choice? As you can see, in terms of the requirements, the requirement table for the class 1 BME, C0G sort of hits all the spots very well. The film propylene hits most of the spots. The only place that you've potentially got to be careful of is the temperature. It doesn't do well with high temperatures and the high frequencies, but it's still a good choice for those that are in the low temperature range. The X7R is there, provides you with the higher capacitor density. In other words, that you get bigger capacitors, and has the low inductance and high DC voltage. So there are opportunities for the X7R technology. But the best technology of all is the C0G and the U2J technologies in terms of what they offer. So let's talk about the power transformers and resonant inductors. There's various opportunities here with either small form factors, the standard platforms. They're up to 5 kV. Again, 500 to 5 kV. You can actually get them. You can get them customized in terms of what you require specifically to your needs, and that is often the situation. And as you can see, there's quite a variety here from Pulse, and that's under the Azure group again. So on the 4th stage, let's move to the final stage, the filter. We're talking about the output inductor, which provides a signal shaping capability in terms of charging the battery. We have the output filters, which is essentially, again, the capacitors, very similar to a DC link, and there'll be the similar ones that we'll use for the DC link, and the power resistors to do the balancing. So let's move through the high power inductors up to 300 amps. Again, another well-stocked range of capability from Pulse. molded power inductors and composite inductors, especially the custom high current solutions available to you in terms of talking with your FAEs and with the salespeople in terms of identifying what the requirements are for your particular design and application. And then we have the filter capacitor. A filter capacitor which has the X7R and C0G, all of these things that have links to them and links directly to the website. If you need to have them PPAP, it is available and available on request. And the output film capacitors, again, it's back to the C4A series. The C4AQ is the original component. We then have the mini, followed by the long life. We've talked about these before. They're exactly the same as before. They provide you with a wide range of choice in terms of what you need, but it's the very same type of capacitor that was used for the DC link and for the DC link and the resonant capacitor in the LLC circuit. And we've been through these before. Again, these are available for you to use as the output capacitors in terms of the last stage of the DC-DC before you actually charge the battery. Again, the AAR70, we've talked about these. It's that rectangular aluminium electric capacitor with the vibration resistance up to 40G and the high ripple current capability, and plus its shape designed to be very economical in terms of putting a whole bunch of rectangular boxes together. Power resistors, again, in terms of the leakage current and maintaining the balance of the voltage of the two capacitors at the final stage. And then one thing that we haven't talked about in great sense is the current sense resistors. There's all sorts of different sizes of resistors that we have available, automotive grade, metal, and the thick film and low ohmic. So you've got a vast choice in terms of resistors available all the way throughout your design in terms of what you actually need to satisfy your requirements to produce those significant designs. So where have we got to? We have got to the safety cap. We'll just go through it and summarize that. We basically got the safety caps for the first stage in the AMI filters from the X caps, the Y caps. We've got the common mode choke to remove the common mode noise. We've got the AC harmonic filter that removes the noise on the AC. We've got PFC inductors that balance the reactive elements. The current sensors, so you can actually understand what current you're actually using and control to suit. You've got the snubbers to protect the switches. You've got the isolation transformers to drive the switches and protect both the switches and the driving circuit. You've got the DC link that actually provides you with the capacitances to fill the energy once you've actually taken it from the AC and converted it to DC. You've got the power resistors that actually balance those particular the DC links. You then got back to the snubbers to protect the switches. You've got isolation transformers to drive the switches. You've got the current sensors to measure the current. You've got a resonant film in terms of the CR, part of the LLC resonant tank. The power transformer to actually provide the isolation between the two sides, and also the self-resonating circuit is a very easy way, low loss and a high efficiency method of actually transferring the energy from the DC side and chopping it up and putting it into a different voltage. And then you've got the output inductors to circuits to filter the signal and provide a signal that's a decent signal to charge the battery. And you've got the output filter as well in terms of that balancing that circuit, that resonant circuit, the output circuit in terms of capacitor and inductor. And we have the power resistors that balance the leakage current and provide you with an even voltage across the two capacitors. And so in summary, you've got a high power conversion webinar identified the key collaboration between the wideband semiconductors and the leading edge RLC components available from the Yageo group. I've listed here, I'm not going to read them all out. You're quite capable of reading them, but what it's basically providing you with is that the wideband semiconductors provide a method of actually going past the silicon and making things more viable in the power conversion sector of the market. You actually need a set of components that are passive components that actually support that type of activity, and you need a wide range of things and wide range of capability. And the history of the company is such that we've been with capacitors, resistors, and inductors for a long time, and therefore know what we're doing. And as we're going towards we can actually develop further solutions and be on the leading edge of providing you with what you need in terms of your requirements to design the solutions that are needed for your marketplace at this moment. And at that point, we'll move into Q&A.